satisfies the definition of group homomorphism. So F is a group homomorphism, and clearly F is onto, because for any n belongs to, sorry, for any 2 raised to n belongs to z, there exists n belongs to z such that f of n is equal to 2 raised to n. So this again onto example 3. Let G is equal to set of all A such that A is an n by n matrix over a real number R, and determinant of A is non-zero, that is the set of all non-zero n by n matrices. G is a set of all n non-zero n by n matrices, non-singular n by n matrices. The group of non-singular matrices of order n over R under multiplication. Clearly this forms a group under multiplication. Multiplication means matrix multiplication, and R star is a R minus singleton 0 is a group under is a group of non-zero real numbers under multiplication. Second group is again group under multiplication. Show that f from G to R star defined as f of A is equal to determinant of A for all A belongs to G is a onto group homomorphism. So for group homomorphism we have to take any two elements from first group. पहिला ग्रुप दिलेला आहे जी मधले कोणते दोन एलिमेंट्स म्हणजे काय आता इथं मॅट्रायसेस आहे. सो एनी टू मॅट्रायसेस ए बी बिलॉंग्स टू जी. सो कन्सिडर एफ ऑफ ए स्टार बी. पहिलं ऑपरेशन इथं सुद्धा मल्टिप्लिकेशन आहे, सेकंड पहिल्या ग्रुपमध्ये सुद्धा मल्टिप्लिकेशन आहे, सेकंड ग्रुपमध्ये. सो एफ ऑफ ए इंटू बी इज इक्वल टू, बाय डेफिनेशन एफ ऑफ ए ची डेफिनेशन काय, एफ डिटर्मिनंट ऑफ ए. सो एफ ऑफ ए बी काय येईल, डिटर्मिनंट ऑफ ए बी. डिटर्मिनंट ऑफ ए बी ला आपण कसं लिहू शकतो, डिटर्मिनंट ऑफ ए इंटू डिटर्मिनंट ऑफ बी. But by definition, determinant of A is nothing but f of A. So determinant of A is f of A, determinant of A is f of B. So we get f of AB is equal to f of A into f of B. Hence f is a group homomorphism. आता आपल्याला याला ऑन टू दाखवायचं आहे. ऑन टू दाखवण्यासाठी काय करावं लागेल, टेक एनी एलिमेंट फ्रॉम R star. So let x belongs to R star. So for that x, we can define this matrix A is equal to x is in first entry, नंतर सर्व एंट्री 0, कॉलम एंट्री 0, नंतर सर्व डायगोनल एंट्रीज 1 0 0 0. जर आता हा we define this matrix clearly. If we can take the determinant of this matrix, this is x, and x is a non-zero because x belongs to R star. Determinant of this is x, so x belongs to G, f of A is equal to determinant of A is equal to x. So for every x belongs to R star, there exists an element A belongs to G such that f of A is equal to x. So f is a onto. Now, next example, let G is equal to Z plus be a additive group of integers and G dash is equal to 1 minus 1. This is a group under multiplication. Then show that f of z from g, f from g to g dash defined as f of n is equal to 1 if n is a even integer, and f of n is equal to minus 1 if n is an odd integer. Then we have to show this is onto group homomorphism. First we have to show it is a group homomorphism. For that, take any two elements from first group, that is mn belongs to z. We have to show this is a group homomorphism. So consider f of m plus n. सो या केस बस यामध्ये आपल्याला दोन केसेस घ्यावे लागतील, कारण इव्हन अँड इंटिजर मध्ये फंक्शन डिफाईन झालेलं आहे. एम बिलॉंग्स टू झेड, एम एन एन बिलॉंग्स टू झेड. सो एम एन एन आयदर इंटिजर और इव्हन इंटिजर और ऑड इंटिजर. पहिली केस आपण घेतो, दोघं इव्हन इंटिजर्स असतील तर एम एन एन आर बोथ आर इव्हन इंटिजर्स. जर दोघं इव्हन आहेत तर एम प्लस एन सुद्धा इव्हन येईल, कारण addition of two even integer is an even integer. So f of m plus n is a even integer, and f of m is equal to 1, f of n is equal to 1 because by definition काय दिलाय, n जर इव्हन असेल तर त्याची इमेज 1 आहे. सो m is even, so f of m is equal to 1, f of n is equal to 1. So again f of m plus n 1 because m plus n is again even. So f of m plus n is equal to 1. 1 can be written as 1 into 1. This one is written as f of m into f of n. So f of m plus n can be written as f of m into f of m. So by definition, f is a group homomorphism in this case. Now for case second, m and n both are odd. दोघं जर ऑड असतील तर दोन ऑड नंबरची बेरीज ही इव्हन असते ऑलवेज. सो एम इज ऑड, एन इज ऑड, बट एम प्लस एन इज इव्हन इंटिजर. सिन्स एम इज ऑड, एफ ऑफ एम काय मिळेल -1, एफ ऑफ एन काय मिळेल -1, बट एम प्लस एन इज ऑड, सो इट कॅन बी एफ ऑफ एम प्लस एन इज इक्वल टू 1. नाउ एफ ऑफ एम प्लस एन इज इक्वल टू 1. 1 can be written as -1 into -1. This -1 is nothing but f of m. This -1 is nothing but f of n. So f of m plus n is equal to f of m into f of n. So now last case. So 1 is even and 1 is odd. You may take m is even, n is odd, or n is even, m is odd. Okay. So but 1 is even and 1 is odd. So m plus n is odd, because even and odd ची बेरीज always odd असते. So f of m is even, so f of n is equal to 1. F of n is equal to -1 because n is odd, and f of m plus n is -1 because m plus n is odd. So consider f of m plus n is equal to -1. -1 can be written as 1 into -1. This 1 is nothing but f of m, and this -1 is nothing but f of n. So in both either cases, f of m plus n is equal to f of n into f of n. So f is a group homomorphism. Also, f of for any two elements, one साठी प्रत्येक वन साठी एक एलिमेंट्स आहे. f of t is equal to 1, f of 1 is equal to 1. So f is again on to group homomorphism. इथपर्यंत आपण डेफिनेशन बघितली ग्रुप होमॉर्फिझमची आणि ग्रुप होमॉर्फिझमचे एक्झाम्पल्स बघितले. नंतर आपण बघणार आहोत पुढच्या लेक्चरमध्ये थेरम्स ऑन ग्रुप होमॉर्फिझम्स.